So it says describe all the solutions of AX equal to 0 in parametric form. So this is more like parametric form. And the non-homogeneous stuff can go in another page. All right, let's get started. So they want us to think about this as a matrix. And for this particular scenario, this is your matrix A. So technically the augmented part is not shown here. So the matrix A has, let me read it, 1, 5, 2, negative 6, 9, 0, 0, 0, 1, negative 7, 4, negative 8, 0, 0, 0, 0, 0, 1, and 6 zeros in the bottom. So we're assuming that the augmented part is 0, and so we're not even showing the augmented part. Okay, is that part clear? So what we can do is we can write it like it was an augmented part and put zeros there, but let's not worry about that. So if this is the matrix without the augmented part, which columns are the free variable columns? So there's pivots. By the way, is this all the way reduced row echelon form? Why not? Okay, so we have a couple of non-zero elements in the pivot columns aside from the ones, so it's not all the way reduced. Although it is in row echelon form, it's not in the reduced row echelon form. So we have free variables. We have 1, 2, 3, 4, 5, 6. There's 6 columns in here, so technically this comes from 6 unknowns. So I think we have 4 equations and 6 unknowns. And we have free variables in x2, x4, and x5. Okay? So if we were to write the solutions to this, and again, remember, we're assuming that this is the augmented part is not included. So if you really want, we can put zeros here at the end for the augmented part. Then your solutions would look like something like this. Our x6 times 1 is equal to 0, so x6 must equal to 0. X5 is free. X4 is free. And now to get x3, I'll put it off to the side over here. X3 times 1 minus 7 x4 plus 4 x5 minus 8 x6 is equal to 0. Right? It turns out that we can use x6 there because x6 is equal to 0. So this whole thing is gone. X4 and X5 are free. So I have to leave that there, and I just solve for X3 and bring everything else to the other side. So x3 is equal to 7x4 minus 4x5. I better start boxing these things. So these are my solutions so far. I have a couple more. I have x2 is free, and now I have x1. So x1 times 1 plus 5 times x2 plus 2 times x3 minus 6 times x4 plus 9 times x5 plus 0 is equal to 0. Okay? So x6 is equal to 0, but it's not there. x5, x4, and x2 are free, but x3 is not. And so I need to rewrite this in terms of x3. So I have x1 plus 5x2 plus 2 times x3, which we found to be 7x4 minus 4x5 minus 6x4 plus 9x5 equal to 0. So I would probably just combine like terms, x1 plus 5, x2. I probably should have brought everything to the other side, but I have 14 minus 6, that's 8, positive 8x4. And then I have a negative 4 times 2, that's negative 8 plus 9. That's just positive 1. And then I can solve for x1. So I have solutions now. I'm looking for 6. Oh, forgot to box x2. I'm looking for values for 6 variables, x1 through x6, and this is what I have. Okay? So if I want to write that in parametric form, maybe I'll write it first as one big vector. And so the x1 is minus 5, x2 minus 8, x4 minus x5. And x2 is free. x3 is equal to 7x4 minus 4x5. x4 is free. x5 is free. x6 is equal to 0. Okay? So that's now written in vector form. Now let's write it in parametric form. And in parametric form, what we want to do is, for each of these, we could break this up into, I guess there's 3 free variables. So I will have 3 vectors with these parameters. So the free variables will be our parameters. We can call them TS, and what's after S? T. Oh, that's backwards. RST. We can call it RST or UVW. I don't know. It doesn't matter. All right. So what we want to do is we want to find the coefficients of x2. So the first one has x2 times negative 5, and the second one has x2 times 1. And then these other ones don't have anything with an x2 in them. That means they must have been multiplied by 0. Oh, and I have one more. Because x6 is equal to 0. I need to have a 6 vector here. This is an R6. Okay? Now let's find out the coefficients of x4, and let's put them down. -8, there's no x4 for that one. There's a 7x4, there's a 1x4, there's a 0x5, so no 0x4 plus x5, and then there's 0 for the 0. And then the last one is the coefficients of x5, which is -1, 0, -4, 0, 1, 0. And they're all 6 vectors. Okay. So we have the solution set for this homogeneous differential equation is looks like it's spanned by 3 vectors. If I randomly choose any number for x2, x4, and x5, then I'm going to get a vector in R6 that's going to work for this differential equation. Okay? The system. Yeah, sorry. I need to shake that out. The differential equation was yesterday. Yes? This solution does not span all of R6. This solution spans a 3-dimensional space in R6. So, you can't visualize it. But let's pretend this is R6. Here, we're only spanning some 3-dimensional space in R6. I wouldn't even call it R3. Let's call it S in R6. So there's a space in R6 that's 3 dimensions, and this solution set spans that 3 dimensions in R6. And one thing we know for sure that it passes through the origin, because 0, 0, 0, 0, 0, 0 is a solution for this. So that's in the solution set, so that must be in that span, which is some 3-dimensional space. Somebody had their hand up? Yeah.
So the better question is, if it were to span all of R6, if we were looking for something that spanned all of R6, then all the variables in that system need to be free, and also fit the criteria that none of them were parallel.
Yeah. Parallel, in quotes.
Right.
Yeah. No, that would never happen, because this is a 6-dimensional. This we have because we're looking for a solution set for a system, and the system has to have at least 1 dimension. How am I going to put that? Nate, maybe you can give it a try. Yeah, so that's the only time it would happen. That's when you're 0. That's when your homogeneous differential equation. That's when your homogeneous system will span all of R6. Is that if everything was 0? But then that means you don't have any equations to begin with. So if you have at least 1 equation, then then your solution set automatically goes down 1 dimension from R6. Because the only way you would be able to, the only way your homogeneous system can span all of R6 is that if all your equations were 0 is equal to 0. And then you won't have equations to begin with. You're not happy. That's because we jumped to R6. Maybe we should come back down. Well, so let's say we're in R3. And then we have a system of equations. So I'm going to make up a system. X plus y plus z is equal to 0. 2x plus 2y plus 2z is equal to 0. 3x plus 3y plus 3z is equal to 0. So this is a system that's going to give us two free variables. I guess what I want to say is that there's no way we can create a system that would give us three free variables with three equations and three unknowns. Okay, so this is 1, 1, 1, 2, 2, 2, 3, 3, 3. And again, because it's homogeneous, let's not worry about the augmented part. And if you row reduce this, you'll get this with two free variables, right? So what we have here is the intersection or the solution for this thing where these three planes supposedly intersect would be at x1 plus x2 plus x3, with x2 and x3 being free variables. So x1 equals minus x2 minus x3. So your solution set is minus x2 minus x3, and then x2 and x3 are the free variables. So we would write minus 1, 1, 0, x2 plus minus 1, 0, 1, x3. So what we're saying is that the solution for this is going to span two dimensions because it's two vectors being combined. And so we can actually see this. Can you see it? So we can actually see this in three dimensions. We have minus 1, 1, and 0 times x3 or x2 plus minus 1, 0, 1 times x3. So in this particular scenario, we have the free variables are going to be parameters u and v. And some programs are s and t. So this is what we have. If we let v grow, let's go from -1. If we let the parameters, the first picture that you saw had the parameters only go from 0 to 1. And so if we let the parameters grow from -1 to 1, this is how it would look like. If we let the parameters grow from -5 to 5, it would be, it'll expand. So this particular program controls your parameters. But as you can see, this is a plane. This is a plane that goes through the origin. And if we take a look at these two vectors, these two vectors would be vectors that are pointing, that are coming from the origin, and that should be exactly on the plane. Can you see them? Oh, you can always reduce something. A matrix can always be reduced in row echelon form. Yes. Because a matrix can be reduced in row echelon form, and it has a unique reduction if it's in a reduced row echelon form. You can always do the matrix, you can always do the row reduction to get it into row echelon form. Yes. Yes. Yeah. Our x1 is not a free variable because in the reduced form it's a pivot. It's a lead. There's a lead non-zero. If there's a non-zero element in a row, then that's a pivot. After you've reduced it, if there's a lead non-zero, then it's a pivot, and that's not free. Yeah. No, it wouldn't mess things up. It's easier by convention to always start with your free variables at the end because a row reduction starts, where a row reduction starts from the left side. Okay. Wow. Is that pretty heavy? Hmm? Well, they're just people who sat and think about. Uh, yeah. Chris, you have a.
Yeah, so with the idea that at least one of your variables has to be fixed, tied into the definition of what a homogeneous linear system looks like. One of them is going to be fixed for sure. You can guarantee yourself that. That's why, like in this case, you have a 3x3 matrix. You're only going to span R2 because one of those variables has to be fixed.
Yeah. Yeah, you can always solve for one of the variables. Okay. Ooh. Let's move on. Let's take a look at homogeneous systems now, or non-homogeneous systems. So homogeneous system is a system where it's zeros on the right-hand side. So you would guess that a non-homogeneous system would be a non-zero vector on the right-hand side. I guess it doesn't. I don't have it in my notes. So let's just say ax equals b, where b is not the zero vector. So that's a non-homogeneous system. And what's interesting here is to find out what the difference is between a homogeneous system and a non-homogeneous system. So that's the main idea here. So let's see if we can pick out a problem and solve for it, and then look at the homogeneous system and compare what we get. Let's do number 9. Let's go back to a nice 2x2 matrix. So let's do this for an example. So this is a homogeneous system. We have A, just we don't need to write this out, but let's just say, just for observation purposes, A is equal to 3 minus 9, negative 1, 3. And then B, the non-zero B is 6, negative 2. So just as an aside, that's what we got. And then I'm going to use a program to row reduce, because remember, I'm done row reducing. That's 3 minus 9 and 6. Oh. Negative 1, 3, and negative 2. So the whole bottom row looks like it got wiped out. So this is our result after some reducing. So it looks like let's see. Let's take a look at some of the possible outputs here. Is this a consistent system? This is consistent, right? Because we don't have 0, 0, and then a non-zero, so this is consistent. It's a consistent system. Does it have exactly one unique solution, or does it have many solutions? So we have at least one free variable. We have exactly one free variable, so I have many solutions. So let's figure out what our solutions are. So this is a free variable. X2 is free. So x1 is equal to x1 minus 3x2 is equal to 2. So x1 is equal to 2 plus 3x2. Okay? So that means our solution looks like this. So our x solutions would look like 2 plus 3x2, and x2 is free. So that's just x2. How can we break this up? Looks like we have a parametered 2, 0, and then we have a vector that's being multiplied by x2, right? So that's the coefficient of x2 is 3 for the first one. The coefficient of x2 for the second one is 1. So this is our parametric solution for this. Okay? So that part was pretty easy, the calculation and the getting the answers and stuff like that. Now let's see if we can actually dig down and see what's happening to this particular system and explain ourselves. We know all about 2x2 systems since we've studied algebra. And so if we take a look at these two equations, we're going to get 3x minus 9y is equal to 6, right? Now, if we look at this equation over here, this is an equation that says if we change this into a t parameter, we can write the equation 2 comma 0 plus t times 3 comma 1. So that's our equation. Now we can draw this by first going to the point 2 comma 0. Where's 2 comma 0? That's on the x-axis, right? And then from 2 comma 0, we're going to have t times 3 comma 1. So 1, 2, 3 comma 1. I should probably draw this in the graphing program instead of trying to draw this by hand and get something that's a little bit more precise. In any case, this is at the point 2, 0, and this, if t is equal to 1, this would be at the point 5 comma 1. And this vector itself here is the vector 3 comma 1. right? So this vector, when you say t times this, you can let t to be whatever it wants. So when t is equal to 0, you're here, right? When t is equal to 1, you're here. This is what your parameter t is doing. When t is equal to 2, then you just double the direction. And then when t is equal to -1, you're down here. You're just going the opposite direction. -1. Okay? So when you parameterize this, you're parameterizing this and you're coming up with an equation of the line. I guess it would have been nice if we figured out what the y-intercept was. But if you look at the line that we got in the beginning, solve for y is equal to 3x minus 6 divided by 9. Is that right? The negative, switch. The free variables. Okay. Yeah. So 2 free variables. Just imagine that you'll span more of it. So if you were to graph this, you should see the exact same graph, because that's what that, this looks like it's consistent and dependent back in the language of algebra, systems of equations in algebra, which means these two lines are exactly the same. Now convince yourselves that if you were to write minus x plus 3y is equal to -2 and write that in y in a slope-intercept form, that you'll get the same thing. So let's actually graph it and see what's going on. Question? Yeah, yeah, correct. In fact, we'll dig more into that 2, 0 vector there. Okay, so if we were to graph, what is it, 3x minus 9y is equal to 6. That's this line, right? So let's draw a couple of vectors. This vector, really hard to see. I guess if we take away the axis, it's right here. Can't make it any thicker. So it's right there, going from 0 to 2, and then if I were to draw the vector from 0 to 5, 1, I would have this vector over here, right? So if I were to come up with that equation, what's that? 3, 1? And let my t is only going from 0 to 1, so if I let my t go from -1 to 2 or something like that, then I would be able to see a little bit more of it. Okay? So the t is a parameter So if I change this parameter into some changing parameter, you see the point? Oh, the point's all the way over here. So depending on what t is equal to, right, it's going to be going up and down along that line. And that's the exact same line as the line that we were talking about. All right. So the parameter makes it so that you can adjust that one number, or two if you have two parameters. You can adjust those numbers and be in the solution set. So that means if I pick this point right here at point 7.6 and 1.8, then that means if I put those x and y values into the original system, that I'm going to get it to be a true statement. Okay? Is that okay? Is it making sense, or is it like super confusing? Am I putting too many? Are the pictures messing you up? Yeah, it would be a lot easier to understand if you've done Calc 3, or if you remember Calc 3, um, or if you had a good teacher for Calc 3, right? Yeah. Anyways, so we got the same line for this particular scenario, and that's what these parameterized parameters do. All right, what I wanted to do is I wanted to tie in our system, and instead of having this system, what if I had a homogeneous system? So what does that mean when you're dealing with a homogeneous system, and how's that compared to the non-homogeneous system if you have the same matrix A? So in this particular scenario, we're looking at AX is equal to 0, where A is equal to 3 minus 9, negative 1, 3. Okay? What do you think we're going to get here? Well, let's do it. Let's reduce. If we reduce this, we're going to get, well, not all zeros. Not get two zeroed away. I think this might be 1. This might be negative 3. Maybe. I mean, we could use Octave to do this, but we just did it. So by the way, when you're dealing with MATLAB, you can always arrow up to go back to the previous command and keep arrowing up if you want to go to like 5 commands ago. So I think this is the row reduction for that. Yeah, if I wanted to switch the rows from the beginning. By the way, I have that. Oh, never mind. I was going to say, I wrote a program, a function. It's a simple function, swap, where it swaps rows. So I have my matrix, and then I need to know which rows to swap. So rows 1 and 2. And there's a switch. No. I mean, you can. I mean, if you're a computer science major, you should do it. You should challenge yourself to do it. And if you're not, then you can just copy off somebody. All right, we're here. We have one free variable again. So our x solution is 3 and 1, right? Right? Oh, maybe I should do that. So x3 is free, x2 is free. Oh, this is x2. x2 is free, and then x1 is equal to x1 minus 3x2 is equal to 0. So that gives you x1 is equal to positive 3x2. Anyways, I wasn't doing much work because I knew the answer already. Why, you ask? Because I taught this class before. No, because it was the same as the non-homogeneous one. So the non-homogeneous she goes from 0 to a non-zero vector that you're setting it equal to. But what happens there is that the free variables are always going to have the same vectors associated with them. And then the non-homogeneous one would only have, the only difference between a homogeneous and non-homogeneous system is that you have different color. You have a different starting point. Okay? So that 2, 0 that we were asking, the displacement of that vector displaces the homogeneous system to make it fit a non-homogeneous system. So what we really have here, by the way, if you were to graph 3x minus 9y is equal to 0, then that's just going to be a line going through the origin, right? And the only difference between these things are that offset of the vector. So the green vector is our homogeneous system. The green line is our homogeneous system. The other line is the non-homogeneous system. And that 0, 2 we got after row reducing is the offset vector that brings you out of the 0, 0, out of the origin. Okay? Yeah. You can think about that. Yeah, you can think about it that way. It's a non-homogeneous system translates your homogeneous system out from the origin. Yes. Yeah. It wasn't B. Whatever the result is, the resulting vector after you do the row reduce, that's the vector that offsets your non-homogeneous system. Because if it was a homogeneous system, right? If it was a homogeneous system, then your right-hand side is just going to be 0, 0. If you're a non-homogeneous system, our B, remember, was 6, negative 2, but then the offset was 2, 0 after we did the row reducing. Yeah. All what? We'll, say will contain what? Oh, for the non-homogeneous, right? If I say this is your system and then um, I want it to equal to B, then maybe the system that I'm giving you is just the matrix and not the whole thing. So I'll hopefully make it clear how the problem is given. Any other questions? So you can imagine this in 3 dimensions also. If your solution set happens to be a plane, then the non-homogeneous system will be a plane that's not passing through the origin, but it would be parallel to the homogeneous part. And I think those are. Do you guys have access to the book? Yeah. So here they talk about lines, and then I guess they only talk about. Oh, here they talk about planes also. So the plane, you have a system, you have a solution to the homogeneous system, and a solution to the non-homogeneous system. The same system, but a different B vector, non-zero B vector. Then that means your solution is going to be parallel to the homogeneous system, except it'll be translated away from the origin. All right. Whew. That was fun. All right, let's talk about linear independence now. So we're going to shift gears and go. We're going to skip. We're going to skip 1.6. 1.6 is a section on some applications for systems. And I don't know if I'll come back to that or if we'll just pick off pieces of the applications that we'll see later on and not worry about 1.6. So linear independence. We're going to look at a set of vectors like we've been looking at, and we're going to relate it to columns, of course, but columns of matrices. But first, let's look at it independently as a set of vectors. Independently. Let's look at it as a set of vectors, and we say that the set of vectors is linearly independent if we have the linear combination of them equal to 0, and then we come out with a x1, x2, all the way up to whatever xp is only equal to 0. That's the trivial solution. Textbooks usually define the dependent first, and they define it this way. They say a set of vectors is linearly dependent if the linear combination of them produces a non-zero solution, where at least one of them, two of them maybe, are non-zero. To the C1, C2, or whatever. Yeah. It should be a zero vector. And that's why it's bold, because it's a zero vector. So let's do a couple of simple cases, and I'm just going to make a problem, so these problems are going to be really super easy. And let's start off with just two vectors. So if your V1 and your V2 are equal to these two really simple vectors, you could just look at them and say, oh, they look like they're collinear, right? They are parallel to each other. So you would expect them to be linearly dependent. And the thing is that, can I find constants to multiply each of these vectors by, so that when I add it, I'm going to get 0. So that's kind of like the question. And just by induction, without really solving for this, you should be able to find it, right? I think if I multiply this by 1 and this by -4, so now I've found two weights or two constants, coefficients that are not all 0, that makes this equal to 0. So then our conclusion here is that this is linearly dependent, or this linearly dependent. Yeah, you can think about it as solving for a homogeneous system, and depending on what kind of solution you get, are you going to get the trivial solution, or are you going to get a non-trivial solution? Yeah. So let's do another example. V1 is equal to 1, 2, and V2 is equal to um, negative 1, 5. So now we can't, this is a little bit more difficult to do by inspection. So you might think, oh, let's actually solve for this. And how would you solve for this system? If we do a matrix and row reduce. So let's draw the matrix. 1, 2. Remember, these are vectors. You're looking for, so the vectors become columns. -1, 5. And then we get 0, 0. We take out our MATLAB program. So 1, -1. And the last one is 0. Let's put 0 there. And 2, 5, 0. Is that a 0? Could be a problem. So if we row reduce this, we get a -0. Look at that. Anybody know why that happens? Having a really, really small negative number. Yeah. So your textbook, if you look through your textbook at the end of each chapter, each section, they talk about computer numerical errors and stuff in computer programs. Anyways, here we have no pivot columns. I mean, no free variables. So there's no free variables here. We have pivot columns on each, which means x2 is going to be equal to whatever it is on the other side is waiting for. It's 0. So x2 is equal to 0. x1 is equal to 0. So that's the only way you can get a solution, is that they're both equal to 0. And that is a trivial solution. So since we have a trivial solution, we can say that these two things are linearly independent. Yeah, if you try to solve for this system, you get all zeros, it's independent. So that is what our little next note is saying. The columns of a matrix A are linearly independent, so it's like putting those vectors as columns of a matrix. If and only if the equation AX is equal to 0 has only the trivial solution. So if that's all you get is a trivial solution, and that is everything is equal to 0. Then it's independent. If you get a non-trivial solution, that means one of those vectors, one or more of those vectors may depend on the other vectors. And that's what dependence means. Now we did a really simple example with just 2 vectors, but we'll see if we can do some more. Any questions? Yeah.
So you have at least one vector that is on, say, two other vectors. Definition wise, the vector that's dependent upon the other two can be, it is a linear combination of the other two? Or
Maybe not necessarily. It may be a linear combination of one other one or maybe two other ones. It depends on the situation. We'll see. With two vectors, really just one depends on the other. But when you have more than two vectors, then that gets a little bit trickier. And so we'll see a bunch of examples. Do I have any examples here? Nope. I have to pull examples from the book. All right, let's see if we can do number 2. We have 3 vectors, and we're asking if this is linearly independent. So the automatic thing to do is just put this into a matrix and then solve for it. We could do that. We can also try to solve by inspection if you can. So the general idea is that we're going to ask, is this, can we find non-zero constants for blanks here, so that this linear combination will eventually equal to 0. By 0, I mean a 0 vector. And if you look at the top, you have -0 plus 0 plus -3 times some number that has to equal to 0, right? So just by looking at the first one, it looks like this has to be equal to 0. But then if this is equal to 0, then the 5 here would have to be equal to 0, right? Now, if these two are equal to 0, then this is equal to 0. You can't find anything. So this isn't a surefire way of doing it. This is more like, your observation. And if you're a little worried about the way you observe things, I think you should try this first, but then you should double check to make sure by actually putting this into a matrix. And I'm going to ignore the augmented part, the 0, 0, 0 column. That would have been in the 4th column. And let's see if we could just work this out. So let's RREF. Now I have to write this by rows. 0, 0, minus 3, 0, 5, and 4. 2, minus 8, and 1. And if I row reduce that, I see that I'm going to get just 1s in the diagonal, so no free variables there. No free variables, only trivial solution. So if I only get the trivial solution, then that means this must be linearly independent. Right? Yeah. Yeah. So a non-trivial solution just means not all of them are zero. So maybe three of them are zeros and then the other two are not. Then that means it's still linearly dependent. If there is a free variable, then there is linear dependence, some degree of linear dependence. I suppose we can column those. All right. Let me try something. Let's take these same vectors and let's add another one to it to see if we can still get a linearly independent set. Because right now this set is deep independent, right? So let's throw another vector. Throw three numbers out, except pi. Yeah, let's stick with whole numbers. 8, 4, 12. All right, let's take a look at 8, 4, 12 and combine it with the rest of this. So instead of so now this is going to get a little bit more difficult because now I have four vectors to deal with and I have to fill out four blanks and stuff. So I'm just going to go right ahead and jump to the matrix. So 0, 0, minus 3, 8, 0, 5, 4, 4, 2, minus 8, 1, 12. And then let's see if this reduces to something that has or has not a free variable. We have to do row reduction. Where's my, what's the search? Uh-oh. All right, so RREF, it's the same thing except we're adding another column, 8, 4, 12. So actually, let's take a look at that first. Uh-oh. Yeah, something's up now. All right, I'm just going to switch to MATLAB then. Oh, did I break this one too? There it goes. So I'm going to call this M just to make sure that we got the right matrix. Is that right? So let's do the REF. So wait, do we have free variable? This is not augmented, right? So let's I was hoping to not go into decimals here, but I guess that was inevitable since we randomly chose our matrix. So this is our row reduced form. So we got 1, 1, 1. So these are pivots. So these are our pivot columns. That means if we don't have a pivot column, and this is not augmented, remember? So this is free. So our x4 is a free variable. So what does that mean? That means we get a non-trivial solution And our non-trivial solution is going to have an x4 is free, and this is too much for reducing. So our x3 minus 2.6667 is equal to times x4 is equal to 0. So x3 is equal to 2.6667 x4. And then I can continue to solve for the rest of them. But the point here is that this is a non-trivial solution. So what can you say about these vectors? They're what? So therefore, these vectors are linearly dependent. Okay? What? Why do we care? Because you're in a linear algebra class. Everybody talks about dependence and independence. If you have more columns and rows, you're going to have a degree of dependence. Sure. So these are vectors in R3. Note, or should we say Nate? So if you have vectors in R3, you can have 1, 2, or 3 linearly independent vectors. You can have up to 3 linearly independent vectors. Anything more will be dependent, will be dependent. Guaranteed dependence, because 3 vectors that are linearly independent will span everything in R3, and if you throw a 4th vector in there, then you can always write it as a linear combination of those 3. And that would be minor dependence, mildly dependent. So that's just a special case. And then, so if you have 5 vectors in R3, then you can pretty much say that the set is linearly dependent. Yeah. All right, so more on dependence. I'm probably going to give you some sort of special assignment that would fall under the category of worksheet over the weekend. So keep an eye out for that. I don't know what that means. Keep an eye out for that.